Alright everybody, I will start with our lecture series on lecture number 20 in this optimal control guidance and estimation course actually. So far you have seen this optimal control formulation from calculus of variations point of view, but for here we will see a very different perspective actually. So let us go get started. So this is the first thing is okay. First thing is motivation and fundamental philosophies, what is there in that. Then we will continue with this Hamilton-Jacobi-Bellman theory. Okay. This is the backbone of this dynamic programming. Then we will obviously give some examples and list out certain important facts, and then I will also give some references for everybody to follow actually. Okay. So this motivation and fundamental philosophy is like this. Okay. Alright. The first motivation is to obtain a state feedback optimal control solution. So far what we have seen in calculus of variation and then associated necessary conditions and then 2-point boundary value problem and things like that, if you remember, is ultimately to get a trajectory from a given initial condition actually. Okay. So what you are interested in here is to obtain some sort of a tunnel of trajectories. In other words, given any initial condition, we should be able to find a solution for the control. Now, what does that mean? That means something like a state feedback optimal control. Given a state, you want to find out towards the control actually. So, and remember this control, it need not be a linear function. It can be any function of state. However, given the state, we will be able to compute the control actually. That's more important actually. So, what is the fundamental theorem associated with that? It relies on this very intuitive piece of argument that any part of an optimal trajectory is an optimal trajectory. Feels obvious, but it's little bit involved to kind of see that. That's very intuitively we will show that here. Okay, let's see. We have found out something like an optimal path from point A to point B via point C. Okay, so this is somehow we have already found out the optimal path. Now, what this theorem tells us is any part, even if you take a small piece of this trajectory, is certainly going to be optimal by itself actually. And remember, that is a different problem altogether. Problem starts from A and stopping at B is different from problem starting at A and stopping at C, things like that actually. Okay. So, what this theorem tells us again is if I take any slice of this trajectory, it is going to be optimal by itself actually. Okay. How does the argument goes? Let us see that we find some other path, okay, from point A to C, and from C to B we will follow the same already found optimal path actually. Then what does it tell? What does it tell actually? Now let us see that this is optimal. If this is optimal, then I could have the cost function associated from point A to C is lesser than this path actually. Okay. So in principle, we could have taken this path from beginning to from A to C, the dotted line, and C to B you could have followed, and then this path from this dotted line A to C and then C to B, that would have been our optimal path actually. Okay. But this is not the optimal path because we started with this A to C via this top line, and that we claim that is the optimal path that we have already found actually, and hence this cannot be the optimal path from point A to C. Okay. So, that is a very fundamental intuitive argument sort of thing which tells us that any part of an optimal trajectory is an optimal trajectory itself actually. Okay. So, let us see how do we use this and to derive this HJB equation. Okay. This is famously called as Hamilton-Jacobi equation, but later on this name Bellman was also added to it because of its own contribution actually. So, now it is famously called as HJB equation or Hamilton-Jacobi-Bellman equation actually. Okay. So, the problem is like this. Again we go back to this this fundamental problem. We want to minimize this cost function subject to this state equation. We have initial condition and we have final time fixed, and we also consider XF being free actually. Okay. Very standard thing what we have been considering so far. The only problem here is, only difference here is there is no outside the cost function there is no term. So, that means there is no terminal penalty per se here. And this is purposefully done. I will introduce this terminal penalty slightly later. It does not hurt the derivation to begin with, and later we will try to introduce that also basically. Okay. And also remember the control here is bounded. That means this omega is an admissible set. Okay. And any solution that lies outside this omega we are not interested actually. Okay. However, this omega can be infinite as well. That means, if you really want to formulate a problem where the control variable is unbounded, then this is also feasible actually. Okay. But if it is bounded, for most of the practical application we are interested in bounded set only, okay, then also this formulation is capable of handling that actually. Okay. So, let us see how things how things proceed. Okay. All right. Now, let us assume that we have already obtained an optimal control solution U star, okay, that is already available to us in the state feedback form, and hence the corresponding optimal trajectory X star is also available. Okay. Just for a second, we assume that this control has been found out, okay, which is optimal control already, and associated with that this X star is also available actually. Okay. Then the cost function is a function of the initial state only, and obviously initial time as well actually. Okay. Remember this cost function, okay, if you see that a little bit, this cost function is here. We have found an optimal trajectory and an optimal control associated with that. And remember TF is fixed, so there is no variation on that. So, what remains is initial condition and initial time actually. Okay. So, this needs to be optimized actually. Okay. And let us denote the optimized cost function as something like this. Now, remember, if I evaluate this cost function now, okay, it becomes a function of only T naught and X naught actually here. Okay. So, this cost function what I am getting here, I can denote it as something like V, okay, which is a function of T naught X naught. Okay. Why you are specifically interested in this? If somebody wants to know, this ultimately this X naught is nothing but my current state actually, and T naught is nothing but my starting time. Wherever I am, that is my T naught, and whatever X I am having, that is my X naught actually. So, I want to interpret this problem, entire problem, as something like initial time in initial state actually. Okay. So, this V is defined as something like this. It's everything else is evaluated, just that it remains as a function of T naught and X naught actually. Okay. Now, let us consider a small time step delta t, okay, between T naught and Tf. Okay. All right. So, what you are telling is there is a T naught there. Okay. All right. So, there is it starts with something like this, there is a T naught, okay, and there is a Tf, okay. My trajectory is there T naught to Tf, but what I am interested is T naught to some delta t, okay, and then this one is rest of the time actually, okay. This is what I am interested in actually. Okay. So, this then what I am interested, what needs to be done here is just this V of T naught X naught, which is nothing but an integral. Okay, remember V of T naught is something like this. Okay, T naught to Tf. So, what I have done is this entire segment of T naught to Tf I have divided in two parts. One is T naught to T naught plus delta T, and the other one is T naught plus delta T to Tf actually. So, obviously, this integration formula that we know can be split to something like this. First is T naught to T naught plus delta T, and the second part is T naught plus delta T to Tf actually. Okay. Next, we define something like this. Okay. Okay. So, this is actually a definition symbol because of this PowerPoint version. There is some issue here. So, essentially, we can define it something like this actually. Okay. So, this J naught is actually, I define it as something like this. Okay. So, what happens here is I want to evaluate, I want to analyze this particular thing little more carefully, and rest of the things is my optimal cost anyway actually. Remember this is my optimal cost already. Okay. This is the optimized cost actually. Okay. So, if I have a path from T naught plus delta T to Tf, that becomes an optimized cost from that point of time actually. That will also use it actually. Okay. Now, this particular time, I mean this T naught to T naught plus delta T is my immediate effect of my control, and hence I want to give a little bit more emphasis for that actually. So, then what happens here? Okay. Then by using this fundamental theorem as I told, okay, that means any part of the optimal trajectory is also optimal. What you can claim first is T naught to T naught plus delta T to Tf, that part of the cost function is same as this one actually. Okay, because that is also an optimal path actually. So, this leads to the this kind of identity that V of T naught X naught is nothing but J naught of X star U star. This is coming from the first part of it, okay, and the second part is coming from this side of the thing. Okay. So, this is this is something some people call this as cost to go, and some people call it as utility function and things like that. Okay. So, this is also possible to define. In next class we will see in approximate dynamic programming, those are the things, terminologies used there actually. This is my utility function. Okay, just to repeat, this is my utility function, and this is my cost to go from T naught plus delta T. Okay. Alright, so now what actually? Let's try to analyze this a little more. Okay. Now first thing is this portion. Okay. Now this portion is something like this. Okay. Okay. This portion can be written as this is nothing but an integral, by the way. Okay. Okay. This J naught of x star u star is nothing but that integral there. Okay. This integral. So, this integral can be approximated, or this using these calculus ideas. Okay. What you can do is you can write it this way. Okay. We assume that there is a delta, this L to be smooth over the interval. Obviously, L is a cost, is part of the cost function what we select. So, obviously, it has to be smooth actually, and also delta T needs to be sufficiently small. Okay. And then there is a theorem in calculus which tells us that if I select an alpha properly between 0 and 1, then I can exactly write this equation that way. Okay. It's almost like trapezoidal rule, but it's something like okay. Let me pictorially try to put it for the benefit of everybody there. What you are telling here is there is a function here. Okay. I want to integrate this. Okay. What it tells is there is some value about which I can, if I take the area of this particular rectangle, then this is same as area under this curve actually. Okay. But it is not halfway through or anything, it is just there exists a small alpha, there exists alpha between 0 and 1, so that this is identically equal. Okay. Now, what about the next one? Now, you remember there are two parts actually, one is this part also. So, that part. Okay. We want to take this Taylor's theorem now actually. Okay. So, what is this Taylor's theorem tells us that okay, if there is an incremental function something like this, I can always use Taylor series and write it this way. First is V of T naught x naught. Okay. Second term is for this first order term with respect to delta T and the first order term with respect to delta x. But this delta x naught I can always write it in this way, delta x naught dot times delta T also. Okay. So, this is what using Taylor's theorem and taking up to the first order terms and keeping the higher order terms this way actually. So, next what happens actually. Okay. Now, we combine both the things. Okay. Then what happens is V of T naught x naught, this is the first part. Okay. What we get from that calculus area equality, and this is what the second part what we got from the Taylor series expansion. Now, remember this part, this x naught dot is nothing but my f of T naught x naught, that is from the system dynamics actually. Okay. So, now I get some form of something like this actually. Okay. So, what can I do now? I can very clearly see that there is a V naught T naught x here and there is a V naught T naught here. So, I can actually get rid of these two. Okay. So, if I do that, and then what I do is I take delta T tends to 0. So, I can divide everywhere by delta T and things like that. Remember, higher order terms will have delta T square and things like that. So, delta T square, delta T cube and all higher order terms. So, what happens here, even if I divide it by delta T and then delta T tends to 0, then all these terms will go to 0 actually. Okay. So, what remains here? First term is this term. Okay. Remember, first order delta T's are gone. Okay. So, this is the first term coming from here is the first term. Okay. And coming from here, this term is here. Okay. And coming from here, remember delta T's are all tends to 0. That means all delta T's are gone here. What are remaining is this one. Okay. So, this now you can recognize that as I told you some time back that what you are interested is a solution from current time and current state. Okay. So, all these what you see here. Okay. These arguments can be dropped, this T naught, x naught and all that, you can interpret that as current time and current state. So, these arguments I can drop out and write these expressions little bit neater. But before that I can also define, again this is the definition symbol. Okay, I can define del v by del x as nothing but lambda, and in fact just a comment, this lambda from this definition del v by del x happens to be the same lambda coming from calculus of variations as well actually. Okay. So, this actually gives us some different interpretation for this co-state variable lambda, which tells us lambda is nothing but the sensitivity vector of the cost function, optimized cost function with respect to state actually. Okay, anyway, coming back to that, we just define lambda like that. So, whatever what you see here is nothing but lambda transpose actually. Okay. The only difference here is this v, remember, is not the cost function, it is the optimized cost function. After you find the control solution, after you put it back and evaluate the cost function, that is the optimized value of the cost function actually. Okay. So, anyway, so using this definition of lambda, okay, and dropping the arguments t naught x naught to t and x, what you get here is this one actually. Okay. So, then this equation is famously called as HJV equation, Hamilton-Jacobi-Wellman equation. But also remember what is L plus lambda transpose F. If you remember this part is nothing but this L plus lambda transpose F. Okay, this is nothing but, if you remember, this is nothing but Hamiltonian actually. Okay, but this is not any Hamiltonian. This, because remember there is a lambda involves V and all that. V is an optimal cost. So, this is actually optimized Hamiltonian. Okay. Okay. So, this is what is defined actually. Alright. So, we define this H opt to be the Hamiltonian for the optimum control, and with this definition, okay. So, this del v by del t, okay, plus H opt equal to 0. That's what you can write actually. Okay. Alright. So, that is what you can write here, and you can tell, okay, del v by del t plus H opt equal to 0 actually. That is a very famously called as HJV equation. Okay. Where this H opt, okay, is minimum Hamiltonian, okay, over this constraint set omega. So, this has to be found out first actually, as I told, okay, this optimized Hamiltonian is to be found out, and then you put it back here, and whatever equation you get is called HJV equation actually. We will see examples and all how to do that. So, what is summary of HJV equation? So, first is you define this cost function v of tx equal to that way, and then this v, you must satisfy this equation del v by del t plus H opt equal 0. It is very easy to remember, by the way. All that you have to remember very quickly is del v by del t plus H opt actually, that is equal to 0. But also remember this H opt is optimized Hamiltonian. That means you have to put the definition of Hamiltonian first, L plus lambda transpose F, where lambda is defined to be del v by del x. Okay, and then I mean, you can substitute the expression back in here and get it. I mean, solve it further to get your control in all that actually. How do you do that? I will give examples to demonstrate that actually. Okay. Remember, L contains control and F contains control. So, those control variables needs to be solved as a function of lambda and x, but lambda, remember, is also a function of x actually, because del v by del x sort of thing actually. It will all come in some sort of a state feedback form. Before we move further, there are certain relevant results. Let us first see that. And first result, it tells you that tells us that if omega is infinite, that means we talk about something like a unconstrained control problem actually. Control variable is not confined to a particular finite set sort of thing. Then this H opt can be computed by computing this equation del s by del u equal to 0. That is what we have seen from the other side of the story, from calculus of variations actually. So, if you put this equation del s by del u equal to 0 and solve for whatever control is the control expression as a function of state and co-state x and lambda, then that is how to, I mean, that is the way to proceed actually. You put this equation del s by del u equal to 0, get a control as a function of state and lambda, and then wherever lambda appears there, I mean, wherever control appears here in this equation, substitute it back and try to solve for I mean, some people try to solve for v directly, because this equation is interpreted as a function of v finally. So, you solve it for V, and once you solve for V, then you get your lambda is available, and once your lambda is available, remember all these are available as expressions, mathematical expressions actually. So, once lambda is available, you can get your control from back from this equation actually. Okay. Now, what's second comment? Second result tells us that when TF is fixed and XF is free, if J is like this, okay, the final boundary condition tells us that if you put V of T and X actually, instead of T, T0, you put X, you put TF actually. Okay. So, V of T naught X naught, if you remember, that is the definition starting from T naught actually. Now, what I put is V of TF XF was my boundary condition sort of thing. Then this T naught I will have to put TF, and hence it does not matter TF to TF any integration of any integrand integrating over the same interval happens to be 0 actually. Okay. So, what you are getting here is if TF is fixed and if XF is free, that is what we started with, then this is the boundary condition that we need to use actually. Okay. Now, what about this terminal penalty? That is what I told you. I will talk about that. So, if you have a terminal penalty also, then what happens is if you put TF XF, then this part goes to 0 and you are left out with this part. Okay. So, what it tells us is just the boundary condition that will be differing actually, boundary condition for V basically. Okay. If you do not have any terminal penalty, this happens to be 0. If you have some terminal penalty, then V of TF XF happens to be that function actually. Okay. Now, the third result tells us that if TF goes to infinity, then what actually? Okay. Remember, many times we talked about infinite time regulator problems and things like that. So, then TF is fixed, but it is fixed at infinity actually. Okay. So, if TF goes to infinity, the standard result tells us that del V by del T has to be 0 actually. This is another useful kind of results. And this actually, if you analyze a little bit here, okay, del V by del T equal to 0. And let us imagine a case where you have something like a scalar problem, that means x is a single variable sort of thing. So, if in that case if del V by del T goes to 0, then what you have is an ODE equation really. Okay. So, this del V by del X is nothing but only one state variable, and hence this del V by del X is nothing but dV by dx actually in that case. Okay. So, you put it back, you get it this PDE actually results in an ODE. Okay. So, that okay, that reminds me that this equation, this HJB equation, if you analyze a little bit, this is del V by del T here and then del V by del X here. Okay. So, this is actually a nonlinear coupled partial differential equation actually. Okay. So, this nonlinear coupled partial differential equation is not easy to solve, but it results in that way actually. Okay. But if TF goes to infinity, then this part is 0. And if you have a scalar problem, then it results in some sort of a ODE basically. But also remember that ODE is not a linear ODE, that means that's typically a nonlinear ODE for a nonlinear problem actually. Anyway, we will see examples for that. Okay. So, this is the result that if TF goes to infinity, then del V by del T is equal to 0 actually. First, let us see an example which will clarify our ideas a little bit. So, it is a very simple example sort of thing. You have a standard quadratic cost function, okay, starting from 0 to TF x square plus e square dt, subject to this nonlinear system equation x dot equal to minus x cube plus u. Okay. Initial condition is known of course actually, and it is an unconstrained problem. That means control is not confined to a particular set actually. Okay. Alright, so let us start solving this. So, first thing is the definition of Hamiltonian. So, Hamiltonian is L plus lambda transpose F. L is half of this fellow, half goes inside. So, this is L plus lambda times F. F is nothing but this minus x cube plus u. Okay. So, this one you put it back here. Okay. This L okay, plus lambda times F. There is nothing called lambda transpose here. Lambda is also scalar actually. Now, the second result is because it is unconstrained, del S by del U has to be equal to 0. That means, okay, now what is del S by del U? First term is nothing but U, okay, and second term is nothing but lambda. So, this 0 is nothing equal to U plus lambda, okay. So, what I get a solution is U equal to minus lambda actually, okay. So, that is nothing but minus del V by del X. So, the point here is if I get a solution for V as a function of state somehow, then I can do this partial derivative, okay, I will get lambda after that, and once I put it back, that is negative of that is nothing but my control, okay, E equal to minus lambda, remember that. So, all that it matters is getting a solution for V actually, okay, let us see how to do that. Now, before that you need to evaluate this H opt, okay, H opt is this is the Hamiltonian definition, but remember U is now like this, U is minus lambda and things like that. So, if you put it back, okay, that is what I get as optimum Hamiltonian actually, okay. When lambda by definition is nothing but del V by del X. So, wherever lambda is there, I will put del V by del X. So, my H opt is like this, okay. So, in this particular example, the HJV equation turns out to be like this, okay. So, if I see this equation in V, okay, there is a partial derivative with respect to time and there is a partial derivative with respect to x, which is also squared already actually here, okay. So, essentially this results in something like a nonlinear partial differential equation actually, becomes difficult to solve. And also remember this on the way this V of T of xf is equal to 0 because there is no terminal penalty here, okay, there is nothing here. So, that is 0, that is why this result comes actually V of T of xf equal to 0. Now, this is a PD and difficult to solve. So, here we introduce one more assumption that okay, what about Tf going to infinity, okay. If Tf goes to infinity, then obviously one of the results implies that del V by del T goes to 0. Now, if this goes to 0, okay, as I told you some time back, this entire thing is nothing but an ODE basically. So, this particular ODE ordinary differential equation can be written something like this. Still this is a nonlinear, ordinary differential equation, nonlinear ODE. Okay, ODE is what we got is much simpler than this PD, but still it is a nonlinear ODE basically. So, how do you solve it? Solving it in closed form is also a tricky situation for nonlinear ODEs actually. And one of the ways to solve it is something called power series approximation and all that. So, let us excite that actually. Okay. You see, this is what I have already told there actually. This is an ODE and still difficult to solve, and what you are interested in is something like an approximate closed form solution. Okay. So, one of the ways to explore is power series approach. So, let us explore that. So, what you are telling here is let me write this V of x as something like 5 terms here actually. And writing up to 5 terms is not, you can think that it is not very really actually, because what I am taking here is 0th power, starting from 0th power constant all the way up to 4th order power actually. Okay. So, what I am expecting here is some sort of a good solution, even though theoretically it is an approximate solution actually. Okay. Now, what we need, if you see this equation, we need an expression for del V by del x here as well as here. So, you put that expression, okay, del V by del x is very easy. This term will be nothing, the 0. This is a1, this is a2x and all that actually. So, this dv by dx results in this term actually. Okay. Now, what you do is, I will not do the entire thing, but what is necessary here is just dv by dx is available now. Okay. Now, your HJV equation is like this. Okay. Sorry, this is this equation. So, we put dv by dx whole square, okay, here whatever expressions we are getting, and then we try to kind of equate the powers actually, various powers, and then get a set of coefficient equation sort of thing. Okay. That I will leave it as some sort of a homework exercise sort of thing. So, what is needed is you got the expressions for V and dV, especially for dV by dx. Okay. So, that expression you take it and substitute it in your ODE, okay, so whatever ODE is here, collect various powers of x, and remember right side is 0. So, that means all coefficients has to be 0 actually. So, all coefficients will become functions of these constant actually, whatever constants you are having, and then you will see that this will result in a set of equations in the parameters actually. These coefficients are parameters actually. And if you solve that set of equation, this is what you will get. Okay. what you will get is A0, A1 and A3, A0, A1 and A3 both all these things are 0, A2 is 1 and A4 is minus 6 actually. Yeah, this exercise you can do it yourself and see. Yeah. Now once you do that, okay, once you have it, then you have got an expression for V and expression for del V by del X. So let us go and see that actually. So ultimately what it leads to, okay, if I substitute here, let me do that probably. Okay, I have got V of X, this is equal to, first term remember A0, A1 and A3 are 0, so that I am not taking. A2 is 1, so this is x square, okay, A2 is 1, remember that, by 2 factorial is 2, and A4 is minus 6. So what I got is minus 6 x4 divided by 4 factorial. So that means 4 into 3 into 2 into 1, obviously that is not there. So this 3 to 6 and 6, this one is gone actually. So this what I am left out is something like x square by 2, okay, minus x fourth divided by 4 actually. Okay. Now if I take del v, this is my V of X, okay. Okay. So if I take del V by del X, obviously this from this side of the story, okay. Okay. If I take this expression, so this I turns out nothing but x minus this 4x cube, 4 will go actually, so I will left out with x cube. Okay. This is what you will get, del dv by dx ultimately is x minus x cube. This is what you are getting here. Okay. Now u turns out to be minus lambda. So what happens? U is nothing but minus x plus x cube. Okay. What is happening finally? I mean, you got the beautiful thing is we got a state feedback control, even though it's a nonlinear optimal control problem to start with, and we had no terminal penalty and TF we assumed to be infinity and things like that. But ultimately, it resulted in something like a closed form expression for the controller actually. So given a state, I can evaluate this control and I am done actually. Okay. That's the beautiful thing about HJV equation in general, dynamic programming actually. Now what is, there is some interesting analysis that follows here. Let us see that also. So we started with something like x dot is nothing but minus x cube plus u. Okay. Now u is nothing but minus x. So if I substitute this is my closed loop system. Okay. So if I substitute this is minus x cube, okay, plus u, and then that u is this one. So I will substitute that. This is okay, minus x plus x cube. Okay. So this x cube will get cancelled out. So this what it results is x dot equal to minus x actually. And obviously this is a linear equation essentially. And with minus x, that means eigenvalue being minus 1, and hence the system is stable actually. You can also very quickly realize that this is the solution is e to the power minus t into x naught actually. So this goes to 0 as t goes to infinity. Okay. So that means we got a solution, okay, which is also stabilizing. Okay. Now there is another interesting argument here, so let me point it out also. Okay. What we get here is something like a, okay, the linear equation actually, stabilized linear equation sort of thing. So somebody can also argue that, okay, why going through all these exercise? I mean, you go to this power series expression, have up to fourth order term, have these partial derivatives, put all the coefficients back in your HJV equations, equate the coefficients. That exercise I have not shown that actually. Equate all the coefficients to 0. Solve the equation for the coefficients and then do this analysis to get it there. Ultimately what it is giving? It is giving me something like a stable linear aerodynamics actually sort of thing. So those of you who know dynamic inversion and those you don't know, I can see my other course actually. There are lectures on that. You can also very well argue that I can actually derive this equation coming from dynamic inversion sort of ideas by enforcing this equation to begin with actually. Okay. How do I do that? It's okay, let me see that, okay, can I not solve my control backwards? That means I start from this equation, okay. Let's see, I start from this equation and this equation will give me that this is my desired x dot, but my x dot is nothing but minus x cube plus u, that is my x dot, that is something like minus x, that is what this equation is giving me. So, my u is nothing but minus x, sorry, okay, minus x plus x cube. Okay. Exactly what I got here, whatever I got here is same is what I got here, and here it is just two line expression. I start with this expression x dot equal to minus x, okay, and this is my desired x dot, but my actual x dot is minus x cube plus u. I substitute that and get to solve my control in two line actually. So, okay, so that is what I have written here. You start with something like a stable desired dynamics sort of thing, you substitute k equal to 1 and then substitute your dynamics and get it very quickly actually, results in the same thing. Now, what is the problem here? Okay. The problems are somewhat like this. Okay. This particular solution that you are looking here is really not a good solution. In other words, it is a stabilizing solution, it will do the job, but if you are a little bit clever or something, you can also see that this control expression what you are getting here is actually cancelling out the beneficial nonlinearity. Okay, we will see this. I mean, we have seen this in SDRE lecture also basically. Okay. So, minus x cube is actually a beneficial nonlinearity, because any terms if you okay, x dot equal to negative of x to the power n, okay, is actually as long as n is odd. Okay, this is a stable dynamics actually, because if I take Lyapunov function v of x equal to half x square, and I get v dot is nothing but x into x dot, okay, x into x dot is nothing but x to the minus of x to the power n plus 1 actually. Okay, let me write it cleanly. Okay, what I am getting here is minus of x to the power n plus 1. Okay, that if n is odd, then n plus 1 is even, and then minus of that is certainly going to be something like a negative definite function actually. Okay, so if you see this analysis, it tells us that okay, minus x cube what was here was actually a stabilizing term, and by doing all this we have actually cancelled out that beneficial nonlinearity. Why it happened is because of what we thought actually that fourth order power series approximation is going to do the job, is not actually. Okay. So, if you really want to have a very good solution, probably you could have continued up to something like 20th order or things like that. Even people do sometimes more than that actually. Okay. Now, if you do that, then all the elegance is lost actually. In other words, even if you take about 5 coefficients, the algebra involved, which I did not show here, is quite a bit actually. Now, if you have more and more number of coefficients, your algebra involved will be more and more actually. So, that even for a simple scalar problem, you can realize what kind of algebra difficulties we get into actually. Alright, so these are some comments you can think about that actually. Okay. Okay, this is the observation comments and things like that. So, what I have told already is summarized here. The dynamic inversion control is nothing but the same truncated optimal control solution, and hence the truncated power series approximate optimal control solutions are not that elegant unless a large number of terms are considered in the power series. That is what I told you. If instead of 4th order term, probably you could have taken 10th order, 15th order like that, 20th order, things would have been better actually. But a large number of terms increases the algebraic and computational complexity actually. So, just blindly having more and more terms in the power series is better for the solution property, but it will also give us I mean lot of headaches for getting the solutions actually that way. And as I also told you, like dynamic inversion, the approximate optimal controller actually has cancelled the beneficial nonlinearity minus x cube term. Okay. And a good optimal control solution should have kept this term in the closed loop dynamics. We will also see that how it is possible and all that actually. Okay, how it is possible to do that. This takes me to a different approach actually. Different approach in the sense, this is my own observation, which I mean why this difficulty happened in my own observation is because we wanted to solve for V. Okay, remember this equation, HIV equation, whatever you are telling is ultimately an equation in terms of V. So, we attempted to solve for the variable V actually, which is optimal cost. However, if you just see a little bit more, all our control is a function of lambda, either x or lambda, and lambda is nothing but del V by del x. Okay. So, why unnecessarily going ahead and solving for V? Instead we can just simply solve for del V by del x, and we are done actually. Okay. Because our control is ultimately function of x and del V by del x, remember that, it is not x and V. Okay. So, we stop at the equation where you just simply solve for del V by del x, and then we will see what happens actually. I will give you one example and then an extension of that example also actually. With the same example that we have been talking about. So, this is exactly the same equation and things like that, same example. Okay. So, your u is again minus lambda and h of t is this. So, we have h of t equal to 0 and get this equation actually. The problem here, the previous approach was we substituted for lambda, that is del V by del x, and attempted to solve for V as a power series in fact. Instead of that, we want to solve for del V by del x, which is nothing but lambda. So, what I will do is I will interpret this equation, what I am getting here, as something like a quadratic expression for lambda. Okay. And this is nothing but a quadratic equation. Okay. So, I get my solution, lambda is nothing but this minus b plus or minus that b square minus 4ac all that actually, okay, by 2. So, if I put it there, what I am getting is something like this. So, my control is ultimately minus lambda, remember that, control is minus lambda, and lambda I am getting it as a function of state. Okay. There is a little bit ambiguity here, okay, which you will need to resolve actually. So, what you are having here is u equal to minus lambda is nothing but this minus lambda is this. So, minus lambda is x cube, this is plus or minus. So, we will have minus or plus actually either way. Okay. So, what it tells us, we have to select now, there are two possibilities here and we select. So, what my claim here is we just select the negative one actually. Okay. We select this negative term out of this plus or minus or plus. I claim that if you select the minus term, it is good, as it is also a stabilizing solution actually. Okay. Remember this expression you can never get it as power series expression actually. Okay. This expression is coming out naturally from this equation here. Okay. So, this is what it is, okay, this for a stabilizing solution, and let us select a Lyapunov function. How do you prove that again, that this is a stabilizing solution? So, we select the standard Lyapunov equation, and all that we need to show is V dot is negative definite. So, if V of x is half x square, then V dot is nothing but x times x dot, and x dot is x times x dot is minus x cube plus u. And remember you have selected it as something like this expression. So, I can substitute u as this expression here, and then minus x cube plus x cube gets cancelled out. Okay. So, we left out with this one, and obviously there is a positive square root of this is positive term always, and this is always positive term, and there is a negative sign here. So, V dot happens to be a negative definite function actually. Okay. So, by Lyapunov theory, it tells us that this is a positive definite function and V dot is a negative definite function, and hence what I got is a stabilizing solution, rather asymptotically stable solution sort of thing. And again, those of you know a little bit of Lyapunov theory, and if you don't know, you can see my other course here. There are I think 2-3 lectures on Lyapunov theory itself actually. So, what it tells you is okay, if P of x is positive definite and V dot is negative definite function, then it is asymptotically stable, but it goes a little bit more than that. Then V of x is actually radially unbounded, because as you go for radially away, your function, okay, has to be away and away actually, okay, this kind of thing. So, x and V of x actually, okay. There is no saturation sort of thing actually. So, it is something like radially unbounded actually, and this function is actually globally defined. V of x is globally valid, half of x square, and V dot what you are getting is also globally valid. This negative definiteness is not confined to a particular region and all that actually. So, V is globally positive definite, V dot is globally negative definite, and on top of that this V of x is actually radially unbounded. So, the Lyapunov results tells us that whatever results we are getting is actually global. That means, this closed loop system is guaranteed to be globally asymptotically stable. Okay. So, this is the power of this SJV theory and all that actually. If you get a solution, if you are if you are able to get a solution, there are certain very neat properties associated with that actually. And also remember, this particular solution that you are getting here will not cancel the beneficial nonlinearity actually. Okay, this okay, we put it here. Our closed loop solution, okay, is not there, but I can derive it actually. Okay, that's not a problem. So, our u is like this. So, our x dot is nothing but minus x cube plus u. Okay. So, what it results in is, okay, minus 1 x cube and minus x cube will go, and this it results in something like minus x sixth plus x square. That means, if I take out this one 1x actually minus x into something like x fourth plus 1 and all that actually. Okay. So, this closed loop system has this property of this not cancelling the beneficial nonlinearity fully basically. It results in a nonlinear closed loop a closed loop system which is nonlinear, but globally asymptotically stable actually. That's the more important thing. Okay, this term. Alright, so this example 2, now the extension of example 1 really, and you want to see that, okay, somebody should not think that, okay, this become only minus x cube is there and hence it is happening and all that. And also remember, in my SDRE lecture I have already pointed out that point of time that this is the solution, this is one solution that we will try to derive ourselves actually. So, this is the problem, same problem, we have a quadratic cost function, okay, subject to this nonlinear dynamics. Okay. Now, instead of simply minus x cube, we have x minus x cube actually. Okay. And also remember, this particular problem, this infinite time quadratic regulator with this nonlinear system dynamics where x is a scalar, has become a benchmark example in literature actually. That means, if you have any new technique that you claim that it can solve some nonlinear control problem, optimal control problems and things like that, then probably this is one problem that you would like to try out first actually. Okay. And we will see that in our many cases, including adaptive critique and all that, going back to this equation again and again actually. Okay. Alright, so this is the same approach we will follow. We will first construct the Hamiltonian. Hamiltonian is L plus lambda transpose F. So, L is this part, half of this term, and lambda times F. F is this. It is not only minus x cube, but plus x is also there actually. Okay. So, as I told you in the SDRE lecture, there is a nice interesting thing goes on here. So, this remember, both are odd powers, x to the power 1 odd, minus x to the power 3 which is odd also. So, this term is a positive coefficient, this term is a negative coefficient. That means, this term is actually destabilizing, whereas this term is stabilizing. And if modulus of x is less than 1, that means x is bounded between minus 1 and plus 1, then x to the power q is very small actually. Okay, that means, within that domain minus 1 to plus 1, this term is less dominating compared to this. That means, this will try to destabilize the system. However, when modulus of x is greater than 1, okay, this x q is getting amplified there. That means, if our system dynamics, this stabilizing part becomes dominant actually. Okay. That means, beyond x equal to that modulus of x equal to 1, that means, okay, let me leave that, it is self-explanatory anyway. So, beyond this bound between minus 1 to plus 1, okay, this term is dominating, which will pull the system backwards, try to kind of lead the trajectory towards 0. But as soon as the x value starts becoming lesser than 1, it falls between that zone of minus 1 to plus 1. Okay. So, this term becomes powerful and this is destabilizing actually. Okay. So, this funny dynamics goes on here actually. Once the magnitude is larger, the system property is stable. Okay. I am talking about homogeneous system without control action obviously. Okay. But once it is close to 0, this is destabilizing actually. Again, it pushes out actually that way. So, unless the control is good, we will never go to 0 basically. The regulator problem will never be happening here, because close to 0 there is a destabilizing term here actually. Yeah. So, these are the reasons why it is also kind of a benchmark problem actually. First it noticed by the Kokotovic really in his paper. Anyway, coming back to this, we have a Hamiltonian definition. So, del S by del U, again that term is not perturbed. So, we have 0 equal to u minus u plus lambda. So, u equal to minus lambda actually. Okay. So, what we are having here is H opt, okay, is optimal Hamiltonian is something like this. Once you substitute u equal to minus lambda, you get something like that. So, again Tf goes to infinity and there is no term, no terminal penalty here. So, del V by del T is 0, okay, and then what you will end up with is something like this, H opt equal to 0, and H opt already we have got it this form, okay. So, this is what it is actually. So, again this happens to be a quadratic equation in terms of lambda. So, again we solve for lambda directly like the previous example. All that we are having is these additional terms here actually, okay. So, what you are getting here is lambda equal to that, and hence u equal to minus lambda, okay, this complicated looking expression sort of thing. But again the claim here is if I take a negative sign instead of positive sign, that will result in a stabilizing solution, and again the similar set of proof can be followed, and let us see very quickly. V of x is again that way. So, V dot of x, okay, x times x dot, and x dot is this expression really, x minus x cube plus u. So, I can substitute back there, okay. So, I substitute back. Remember u equal to this expression already, okay. So, whatever u you are getting, you can substitute it there actually. So, x into x dot contains this term plus u, and u is that term already. So, this term, okay, with a negative sign here. So, we substitute all that, and this you can rewrite this expression v dot as something like this actually. And again this term is a quadratic function. So, this is always positive for x not equal to 0, okay. And this is also with a minus into x square sort of thing. So, the v dot is a negative definite function, okay. And again this happens to be globally valid, and again this v of x is radially unbounded. That means, once again we will end up with a situation where this controller that you are telling, this control is this expression, okay, and hence it is a closed form expression actually, and it is this particular state feedback optimal control solution will result in globally asymptotically closed loop system actually, okay, globally asymptotically stable closed loop system. So, that is the power of this HJV equation and all that actually. So, this small example and an extension of this, otherwise these two small examples demonstrate the usefulness of HJV equation actually. However, in general it may not be a very good technique for getting the solutions this way. My suggestion is probably if you can do it, the first attempt should be towards this, but if you cannot do it, there are many techniques getting developed and also developed already, which will try to exploit the HJV equation to get something like an approximate solution and all that actually. Okay, we have seen one solution for theta d approach and all that in the last class actually. Alright, so some important facts are something like this. In general, these are generic facts actually. First thing is like this: dynamic programming is a very powerful technique in the sense that if HJV equation is solved, it leads to a state feedback form of optimal control solution. None other technique gives that actually. And what you are looking at is something like a tunnel of solutions together basically. That means my T naught and x naught can fall in from a domain of values, and I am ready with my control solution for that actually. Okay, so that is the power of HJV equation. Okay, HJV equation also turns out to be both necessary and sufficient. So that means, okay, so far we have not talked about sufficiency conditions and all that in calculus of variation approach. We have always talked about necessary conditions only. But HJV equation, it turns out that is both necessary as well as sufficient. Okay. The last one is, the next one is what it tells us this: even though this HJV equation is a nonlinear PDE in general, and hence it can throw multiple solutions and all that, it tells us that at least one of the control solutions that results from the solution of Hessian equation is guaranteed to be stabilizing. We have seen that examples actually, like we took some Lyapunov functions, positive definite, and so that V dot is negative definite and all that actually. But it turns out that this result is quite valid in general, where it tells us at least one of the control solutions that results from the solution of Hessian equation guaranteed to be stabilizing. That means we don't have to keep on searching and all that. Within the finite set of solutions that we have, we explore which is the solution that is stabilizing, and we are done actually. Okay. All right. Further things, the difficulty part is rather like this. The resulting PD from the Hessian equation is extremely difficult to solve in general. There are that I have been pointing out consistently. And suppose you want to solve it numerically, there are numerical attempts also to solve this Hessian equation numerically actually. It runs into the huge computational and storage requirements for reasonably good practical problems actually. And this turns out to be a severe restriction of dynamic programming in general, which Bellman himself termed it as something like curse of dimensionality. That means, if the number of states are increased or the duration of control application T0 to Tf that is more, then it runs into these huge computational and storage requirements. In other words, the computational complexity is in the form of exponential actually. So, that is what Bellman has termed it as some curse of dimensionality. Okay. Remember the calculus of variation, we had this curse of complexity actually. Okay. The dualization problem and all that lead to curse of complexity. Here it leads to curse of dimensionality. Both are equally bad in a way basically. Okay. So, we will for next classes and all we will see how to come out with this, how to kind of address this curse of dimensionality in a limited sense at least, or in a reasonably good way. Okay. So, that we will get this benefits of this Hessian equation without running into these difficulties actually. Okay. That will result in this approximate dynamic programming, neural network based adaptive critic solutions and all that actually. We will see that in the next class anyway. So, with that I think I will list out a few references here. Most of my material here is taken from this first book, okay. And some of the examples I have solved it myself actually, this benchmark example especially. Okay. And then always you can refer to Weissen and Hu, I mean this is a very standard book, is also a small chapter on dynamic programming actually, but my derivation is taken from Sage actually. Okay, then all these things are available, these two things are available as very good sort of papers which are survey papers in a way. This is a survey of dynamic programming and computational procedures, very old paper, 1967 sort of thing. And of late recently, this is also another one, okay, which talks about nonlinear optimal control of washing machines based on approximate solution of Hessian equation. It results in a closed form expression, but the closed form expression is a very high order, 40th term, 50th terms, 50 terms, 50th order and things like that. It's a very interesting paper. I suggest that you can read and probably try to kind of experiment yourself if you are curious actually. Alright, so with that I will stop. Thanks for the attention.